The next topic for your consideration involves the rank, in particular the rank of a matrix. Let me start with an example to illustrate what this means. So consider the following matrix. I'm just going to count up from 1 to 12. 4, 5, 6, 7, 8, 9, 10, 11, 12. Then the rows are horizontal vectors. In fact, row 1 from that matrix we'll write in the following format: 1, 4, 7, 10. Row 2 will equal 2, 5, 8, and 11. And then row 3 will equal 3, 6, 9, and 12. So the definition: the row space of a matrix, let's say it is an M by N matrix. Then it has n columns, so each of our rows will have n parts to it. So the row space of an M by N matrix is a subspace spanned by the rows of A. This subspace, we'll call it row A, is the name of the subspace. And in our example from above, in the first example, row A is simply the span of those vectors. Let me illustrate. We'll find one of these things. I'll have a more, a heavier example than I just had. So let's see here. We have 1, -2, -3, 3. Then I have -3, 6, 9, -9. I have 4, -6, -6, 4, -1, -1, -6, 9, 9, -10, -3, 0. And what I want to do is figure out the row space of this thing, or better yet, find a basis for the row space of this thing. So let's find a basis for row A. And as you can guess, we're going to do elementary row operations until I'm done. So the first thing I'm going to do is I'm going to use this 1 in the first entry of this matrix to wipe out all the elements underneath of it in that column. So in order to do that, I have to do 2R1 plus R2, 3R1 plus R3, and then negative 3R1 plus R4. So as suspected, it will wipe out the entries underneath of that one. The first row is not affected by this operation, but the next ones will be. So let's see what we have going on here. 2 times negative 3 is negative 6. 2 times 4 is 8. So minus 6 will be a 2. 2 times negative 1 will be negative 2, and negative 1 will be negative 3 there. And then 2 times 9 is 18, minus 10 gives us an 8. And now 3R1 plus R3 will zero out this entry right here. And then, let's see, 3 times 4 is 12, minus 6 is 6. 3 times negative 1 will be negative 3, minus 6 will be negative 9. And 3 times 9 minus 3 will be 24. Now let's move on. Then I'm doing negative 3R1 plus R4. So negative 3 times negative 3 is 9, which cancels that negative 9. Then negative 3 times 4, we have negative 12, plus 4 is negative 8. And then negative 3 times negative 1 is positive 3, plus 9 will be 12. And then negative 3 times 9 will be negative 27, plus 0 will be negative 27. All right, next what I'm going to do is I'm going to use this 2 right here to wipe out the numbers above it and below it. So to do that, I'm going to do negative 2R2 plus R1. And then I'll do negative 3R2 plus R3. And then finally I'll do 4 times R2 minus 8. Well, I'll do 4R2. That'll wipe out that thing. So 4R2 plus R4. And let's see what we get for our new matrix. Now the first 2 columns will be unaffected by all this. And for the next one, I have designed this so I clear out everything except the 2. Now let's see what happens in the other rows. Okay, so negative 2 times negative 3 is positive 6 minus 1. That will give me a 5. Oh, I should keep in mind that the second row is unaffected by all this stuff. Then negative 3 times negative 3 will be positive 9. Minus 9 will go to 0 there. And then 4 times negative 3 will be negative 12, plus 12 will be 0. And then let's see what happens on the last column here. Negative 2 times 8 is negative 16, so we'll get a negative 7 there. And then negative 3 times 8 is negative 24, plus 24, put a 0 here. And then 4 times 8 be 32 minus 27, we'll put a 5 here. And the last thing that you'd want to do is swap rows 3 and 4. So I'll do row 3 swapped with row 4. And from this, notice what we have now. We have a 1 pivot column, 2 pivot columns, 3 pivot columns. But in the same vein, look what's also going on. These leading numbers are the pivots. They also happen to be the leading ones, or the leading non-zero items in the rows. So what if we thought of these as pivot rows? So the row space will be spanned by 3 vectors. I swapped vectors 3 and 4, so keep that in mind when we go back to find the original vectors that were in each of these rows. So let's start with what was the first row, and that was 1, -3. I think I had a 4. And then I have -1, 9. The second row was -2, 6, -6, -1, and -10. And then the third row, well, remember it was in the fourth row. So we actually went, not the third row, but I went the fourth row, 3, -9, 4, 9, 0. So 3, -9, 4, 9, 0. And there's how you get it. It's very similar to columns. In fact, you're looking for exactly the same pivots for this as you were for the columns, because they both go off of the leading number. And it's easy to spot either row or columns this way. You might find this theorem convenient for computing the row space of A. Here's how it goes. If A is row equivalent to B, these are matrices, of course, then their row spaces are the same. Now, furthermore, if B is in echelon form, then the non-zero rows of B are a basis for row A. Proof. Well, what we're going to have is that A will be row equivalent to B. So what does that involve? We can add a multiple of one vector or one row to another row. We can multiply a row by a non-zero scalar. And what else can we do? We can swap rows. So those are the 3 things that we can do to go from A to B. We can do any of these 3 things as much as we want until we get there. So with that in mind, if you considering that row A is a subspace of some r to the n. I don't know what the n is, but I know it's a subspace of that, all I care about is that is a vector space. It is, let me call these 1 and 2. It is closed under 1 and 2. For 3, that's no big deal. We just swapping vectors in a basis doesn't change anything. So I start with row A, do these 3 things to it, which doesn't affect it at all, and I somehow end up at B, then row A and row B must be the same because all of these things still produces vectors that are in row A. In fact, all this says, this all means that row A is a subset of row B. On the other hand, you can always reverse this stuff in the opposite direction to go backwards, so I don't really need this subset at all. Let's just make it equal. Now for the second part of this, put the 0 rows at the bottom. Well, then the rows, then the non-zero rows, each of those will begin with some sort of a non-zero number, right? So even if you had something like this, I don't know if we had something like this, and then this next row went like this, and then I don't know, maybe there was some space here and the next row went like this, etc., until we eventually got down to a row of zeros, you know, to finish things off. What would happen when we put them all down there? The fact that it's an echelon means that as we progress from one row to the next row, the first non-zero term has to be to the right of the last non-zero term, but from the previous row. The reason why is if I have them stacked up, then I can use the non-zero, the leading non-zero term, the pivot if you will, to wipe out the items below and above it. So we can see that if we put the rows at the 0 rows at the bottom, the non-zero rows will form. So basically you'll find the non-zero rows will form the basis for B, which will, that's row B, which will form a basis for row A. And the first thing I wanted to do then is redo that first example and find the row space of the given matrix. So in our first example, what do we have? A was equal to, I think it was a 4 by 5, 1, negative 2, negative 3, 3, negative 3, 6, 9, negative 9, 4, negative 6, 4, negative 1, negative 1, negative 6, 9, 9, negative 10, negative 3, 0. If you recall what we ended up with, So it would be B in the theorem. Well, the beauty of this is that now my row A does not have to be listed just in terms of the original vectors. I can use these vectors here because they're linear combinations of these vectors. And a vector space is closed under linear combinations. So it'll be the span of the first, well, the three non-zero vectors, 1, -3, 0, 5, -7, 0, 0, 2, -3, 8, and 0, 0, 0, 0, 5. Definition: the rank of a matrix is the dimension of its column space. In other words, so just in symbols, rank A, this is the notation, will equal. In fact, I believe that a lowercase r is used for the rank. I don't know why, but rank A is equal to dim column A. And this leads us to a theorem that has a name. So you know what that means. Be careful. Memorize this, whatever you got to do. This is an important one. Any theorems with names are important. So what we're going to do is we'll start with let A be an M by N matrix. Then the rank of A actually also equals the dimension of the row space. So this means the dimension of the row space is the same as the dimension of the column space. Very nice. Just a notation here. Let me say note. This won't affect us for the most part. In some books, nullity of A is used for null A. But we'll just use null A for what we're doing right now. And the reason I mention that is, remember we have this equation, rank A plus dim null A equals the number of columns. Let's prove this. So we know that the rank of A is the number of pivot columns in A. The number of pivot columns equals the number of pivots. I'm not saying anything extraordinary there. if B is an echelon form of A, then the non-zero rows each begin with a pivot. Thus, the number of pivots is the dimension of row A. Therefore, rank A equals dim row A. Now, next, if I look at the dimension of the null space of A, that's equal to the number of free variables in the equation AX equals the zero vector. Well, that's simply that is dim null A is the number of non-pivots in A. But the number of pivots plus non-pivots, so pivots, let's put number of pivots plus number of non-pivots equals the number of columns. This is pretty clear. You're either a pivot or you're not a pivot. So we're one or the other. But then the number of pivots we know is to be the rank of A, and the number of non-pivots, of course, is the dimension of the null space. Let me do some examples to illustrate some of these numbers. This, one of the things, when I've done this before, what happens is so many numbers get thrown around that your head can spin if you don't try to keep track of these things. So let me sort of illustrate some of the patience that'll be required, or some of the thoughtfulness that'll be required when you're doing some of these problems. So let me start with a 6x3 matrix. And let's suppose the rank of A equals 3. Then we have the rank of A plus dim null A equals, let me see, it's got 3 columns. This is equal to 3. Well, the rank of A was equal to 3. This tells me the dimension of null A equals 0. In other words, null A equals simply the 0 vector. Well, while we're at it, the dimension of the row space equals the rank, which equals 3. By the way, here's an interesting thing you should take a look at. You should, let me make a note here. The row space of A is no different than the column space of the transpose of A. So that should make sense. Well, then if I look at dim row A will then equal rank A transpose. But I already know that dim row A is equal to the rank of A. So that's an interesting result right there. Another example. This time I'm going to let let A be a 5 by 6 matrix. And suppose A has 4 pivot columns. Then, well, if since it has 4 pivot columns, we know that the rank of A is equal to 4. So then the dimension of the null space of A is equal to the 6 columns minus the rank of 4, which is equal to 2. Also, keep this in mind. Here's another thing to notice. Notice that the columns of A are vectors in R5. Basically, the number of rows of A tells us what space we're dealing with. So each column has 5 rows. So the columns of A are vectors in R5. And by seeing that the rank of A is equal to 4, we see so the column space of A is isomorphic to R4, but column of A does not equal R4 because column of A is a subset of R5. Let A be a 7 by 6 matrix. And let's let the dimension of the null space of A equal 5. Well, then our rank of that matrix will be the number of columns minus the dimension of the null space. Another example. Let's let A this time be a 5 by 6 matrix. And dim null A this time equals 4. So the rank of A will be the number of columns minus the dimension of the null space, so that will be 2. Notice this also implies that the dimension of the row space equals 2. Next, suppose A is a 4 by 3 matrix. What is the largest possible value of dim row A? Well, this is interesting. You might say, well, you could have 4, but you can't. The highest you could have is 3 because the dimension of the column space is less than or equal to 3. So let's take a look at this. The rank of A is less than or equal to 3, which implies that the dimension of the row space is less than or equal to 3. So the maximum possible size you could have for, or the maximum possible value you could have for the dimension of the row A is 3. So I guess I should put the answer is, what is, there's a question mark there. The answer is 3. All right, this time let's let A be a 3 by 4 matrix. What is the largest possible value of dim row A? Well, in this case, it's going to still be 3 because the most number of rows we can have is 3 in here, but we could have 4 columns. Now, obviously, we can't have all 4 of the columns be linearly independent because the rank is also equal to the dimension of the row space. So let me get this settled down for you here. We have the rank, the dimension of row A is less than or equal to 3 because we have 3 rows. And we could have up to 4 linearly independent columns had I not known about this 3. So keep in mind, this also means that the max value for the rank of A is also 3. Here I'm going to let A be in mk by n, where k is less than n. Then what we know then is that dim row A is less than or equal to k. The n's bigger, so I am limited only by the number of possible rows that we have. This implies that the rank of A is less than or equal to k as well. Now also, since dim row A is less than or equal to k, and k is less than n, we must have that dim null A is greater than or equal to 1. I'll show you what I'm talking about here. Let's see, we have, well, let me use this. We have the rank of A plus dim null A which we know together they've got to add up to n. But let me put in my inequality here, but dim null. But the rank is less than or equal to k. This implies that the dimension of the null space of A is greater than or equal to n minus k. Since n is greater than k, this here is greater than or equal to 1. So no matter what, you're going to have some non-zero vector sent to the 0 vector when, well, some solution, some non-zero vectors will be in the null space. That means when you multiply them times the matrix, you'll get 0. Let's let A be a 6 by 4 matrix. What is the largest possible value of dim null A? So let's see what we have here. A is in M 4 by 6. So we know that if I take the rank of A plus dim null A, and that is supposed to equal 4. So can we have the rank of A equal to 0? I guess if the matrix is 0, you could have that happen. But nonetheless, we have solution. We do know this, that 0 is less than or equal to the rank of A, which is less than or equal to 4. Now, I can't imagine, the only way you're going to have 0 is for the matrix to be the 0 matrix. So the rank of A really is always going to be at least 1. So if I say it's a non-zero matrix, that changes things. So if M is the 0 matrix, I don't know what kind of notation to put for that, then that's when we get the largest possible size of the dimension of the null space, and then it will equal 4. But anything else, of course, is just going to take away from that. Take a minute to read what you have here. We have a matrix, so what we're going to do is I'm going to let my matrix A be in M 5 by 6. How do I know that? We have 5 equations, so I have 5 rows. 6 unknowns means I'll have 6 columns. And the solutions of the homogeneous system, so this version, the solutions to this are all multiples of one non-zero solution. So what does that mean? This right here, all multiples of one non-zero solution, means that the dimension of the null space equals 1, since one vector gives us all the solutions for those. So, will the system necessarily have a solution for every possible choice of constants on the right sides of the equations? So, if I look at this, will I always have a solution for AX equals B? Well, let's take a look at some of the things that we have. We have, let's take a look here, the rank of A plus the dimension of the null space of A, we know is equal to the number of columns. That's this. So I know that equals 6. Now I've just been told dim null A is equal to 1, so I know that the rank of A equals 5. Now think about this. We have 5 equations. So since A has 5 rows, each column is a vector in R5. But I just found out the rank of A equals 5. So that means, well, what does it mean then? So that means the dimension of the column space of A equals 5, but column space of A is a subspace of R to the 5. But the dimension of R to the 5 is 5. So this must mean that the column space equals all of R to the 5. So no matter what we put on this side, it's going to be a vector in R5. Well, I just found out that column of A is all of R5. That means that it spans all of R5, no matter what B is in. So since B has to live in R5, and the columns of A span R5, there must be a solution. For any B in R5. Recall, the AX is simply a linear combination of the column vectors. So I guess the question actually asks us, will the system necessarily have a solution for every choice of constants? Yes, it will. The answer to the actual question is yes. It's because of all this stuff here. So since the columns of A are R5, they span all of R5. That means that some linear combination will equal any B that you can possibly come up with. So you can see that we have here a slight connection between rows and columns, not as much as I was looking for, but let's do some more of these problems here. Okay, we have a non-homogeneous system of 6 linear equations in 8 unknowns. So what I have is a system like this. Non-homogeneous means that B is not the 0 vector. Okay, A is what? 6 equations, so 6 rows and 8 unknowns, 8 columns. We have 2 free variables, so 2 free variables that means that the dimension of the null space of A is equal to 2. The number of free variables is the same as the dimension of the null space. So let's see what they're asking us. Is it possible to change some constants on the equations right side to make the system inconsistent. So is it possible to come up with some B, if you will, to make this system not have a solution? So let's put it this way. Does there exist B? Now, where does B live? Since we have 6 rows, B is in R6. Now let's take a look at what we have. We know that dim null A is 2, so rank of A plus dim null A, we know equals the number of columns, that's 8. But I was just told that dim null A is 2, so the rank of A equals 6, but A is in the columns of A is in R6. So the column space of A is a subset of R6. But here I see that the dimension of the column space is equal to 6. Column of A is equal to R to the 6. Since its dimension is 6 and it's a subspace of a space whose dimension is 6, well, we know that therefore it has to equal the whole subspace. And so does this mean can we possibly make the new system inconsistent? Well, if column of A is equal to R6 and B is in R6, then B is necessarily a linear combination of the columns of A. So B is a linear combo of the columns of A. No matter what. So what is the answer to this? Is it possible to change some constants to make it so that you don't have a solution? No, the answer to this question is no. All right, this time we have a non-homogeneous system of 9 linear equations and 10 unknowns. So we're looking at this. AX equals B. Since it's non-homogeneous, B is not the 0 vector, and A is in the set of matrices with 9 rows and 10 columns. 9 equations means 9 rows, 10 unknowns means 10 columns. So suppose it does have a solution for all possible constants on the right side of the equation. So this has a solution no matter what the vector of B happens to be equal to. Is it possible to find 2 non-zero solutions of the associated homogeneous system that are not multiples of each other? Let's find out. Okay, so is it possible to find 2 non-zero solutions of the associated homogeneous system? So that's this. Well, let's take a look here. So this is then going to tell us what the dimension of the null space is. Let's do my basic formula here. The rank of A plus dim null of A is supposed to equal 10, the number of columns. And since we're told that we have a solution for all possible constants, then the dimension of the column space has to be 9, because B can be any vector in R9. The columns A have to span R9. In other words, we are told that the dimension of the column space must equal 9. But then that implies that the dimension of the null space is going to equal 10 minus 9, which equals 1. That means that null A is spanned by exactly one vector. I'll call it n just for convenience. So then, is it possible to find two non-zero solutions of the homogeneous system that are not multiples of each other, that are not? Well, unfortunately, all the non-zero solutions are all multiples of this one particular n. So the answer is no. There's a sense all the solutions to AX equals 0 are all multiples of a single vector. Next we have, is it possible that all solutions of a homogeneous system, so once you see homogeneous, you're looking at a system like this. And always, when they're talking about that, you immediately want to start focusing on the null space. We have that A is in, let's see, 10 equations in 12 variables. So it is a 10 by 12 matrix. And what does it say? Is it possible that all their solutions are multiples of one fixed non-zero solution? So is that possible? So is it possible for dim null A to equal 1? That's what the question is asking us for, because we're talking about the solutions to this homogeneous system. Those non-zero solutions are all going to be members of the null space of A. So anyways, let's take a look at our basic equation here. In terms of A, we have the rank of A plus dim null A. That has to equal the number of columns, which is 12. Now, is it possible for dim null A to equal 1? So if then we have rank of A will equal 11. Is it possible for the rank of A to equal 11? Well, the answer is no. Unfortunately, the rank of A equals the dimension of the row space of A. Since we only have 10 rows, the row space of A can't be any more than 10. So the answer to this question is no. This cannot happen. Next, we have a homogeneous system of 12 linear equations and 8 unknowns. So we're looking at something like this. AX equals 0, and A is in M 12 equations, 12 by 8, like that. And it has two fixed solutions that are not multiples of each other. So if that's true, what they've told me here, two fixed solutions that are not multiples of each other. This right here, I'll include this part too, tells us that the dimension of the null space is equal to 2. So we have the rank of A plus dim null A equals 8. And then rank of A would equal 6. All right, if rank A equals 6, we know that the column of A is isomorphic to R6. Now the question asks us, can the set of all solutions be described with fewer than 12 homogeneous linear equations? Well, of course. We only need 6 rows, which implies 6 equations are all that we'll need. Next, is it possible for a non-homogeneous system of, so non-homogeneous, we're going to have AX equals B. B is not the zero vector since it's non-homogeneous. A is in M7 by 6. So we want to have a unique solution for some right-hand side of constants. So let me answer that part first. There's 2 questions here. Is it possible to have a unique solution for some right-hand side of constants? So let's see here. We have 7 equations, or 7 rows and 6 columns. Well, to have a unique solution, we need 0 free variables. Those are the things that give us an infinite number of solutions. So 0 free variables, that tells us that the dimension of the null space is equal to 0. Well, let's take a look then. Rank A plus dim null A equals a total of 6. And since I am assuming dim null A is 0, rank A is equal to 6. Now I think about it. If rank A is equal to 6, then we know that the column space of A is isomorphic to R6. But the column space of A actually lives inside of R to the 7. So there are vectors in R7 that are not in the column space. Well, that's because the dimension of column of A is 6, dimension of R to 7 is 7, so naturally there are vectors in here that are not in column of A. If my B's are something like this, let's say it looks like, where are we at, R7? Okay. Say B1 up to B6, but then it has a 0 in the 7th spot after echelonization. Then we can have a unique solution. because then the rank of A is equal to 6, which means the row space is equal to 6. That means we'll be able to have 6 non-zero rows when all this echelonization is done, and then we'll have a nice 6 by 6 matrix. It can be invertible since we'll have the dimension of the space will be full 6, and so therefore we can have a solution in there. However, if your B looks like this, up to B7 after, if you try to look up the word echelonization anywhere, you'll not find it. I'm making it up. But anyway, if you see something like this after echelonization where each BI is non-zero, then you won't have a solution. In particular, what will happen is you'll get a matrix that'll look something like this. You'll have your B's, B1, B7, but then when you go to the echelonization here, on the other side, you'll get a bunch of zeros on here. How many was it? That was in 6 columns. So 1, 2, 3, 4, 5, 6. Instead of an equal sign, I should probably put that line that we put down there for augmented matrices. So you'll have equation 1 through equation 6, but then you'll have something like this. And if that B7 is not 0, then you're not going to have a solution. So the question is this. Let me go and answer these. There are 2 questions here. Is it possible for it to have a solution? So the answer to the first question is yes. But is it possible for such a system to have a unique for every right-hand side? The answer to that part is no. Now let's see, we have a scientist solves a non-homogeneous system of 10 linear equations in 12 unknowns. So he is solving AX equals B. The B is not the 0 vector. And A is a 10 by 12 matrix. Now we are told that 3 of the unknowns are free variables. So that right there tells us that dim null A equals 3. So let's go back to our equation. Rank of A plus dim null of A equals 12. I'm just told that the dimension of the null space is 3, so this will imply that the rank of A will equal 9. Now, can the scientist be certain that if the right side of the equations are changed, that means I start playing around with different B's here, the new non-homogeneous will have a solution? No, not in this case, because if you look at it, we have rank A is 9, so that means that the column space of A is isomorphic to R9. Now, unfortunately, column space of A is a subspace of R10. So, we're here, then column of A has the dimension of 9. The dimension of R to the 10 is 10, so there are vectors that are outside of A. So, there are So in other words, no, they can't be certain. So the answer to this is no. So keep that in mind. Dimension of this is 10, dimension of this is 9. There's automatically stuff inside of here that's outside of here. So in order for AX to be AX equals B to be consistent, so that is consistent if there is a solution. Doesn't say unique solution, just a solution. That's all that means. So anyways, so to have any kind of a solution, what must be true? Let's see what we have here. Suppose A is m by n and B is in r to the m. What must be true about those numbers? So let's take a look at rank. AB is basically, we would have what? We had n columns of A, so this is the same thing as rank C1, C2, up to Cm, and then we have this B vector here. Cn, there are n columns in A. All right, for any time for there to be a solution here, we need to have a solution always B must be in the column space of A. So if that's the case, that means that B is a linear combo of the vectors, the column vectors in A. Well, if that's the case, if B is a linear combination, then adding B to this collection of columns did nothing, because this B is a linear combination of all those things. Let's see, if B is in column of A, then B is in the span of C1 up to Cn. But that's no different than the span of C1 up to Cn and then attaching B, because it just gets absorbed by the C's. So rank A with the B vector attached is the same as rank A. Explain why an M by N matrix with more rows than columns has full rank if and only if its columns are linearly independent. So we have more rows than columns, so what do we know? We know that M is bigger than N. Full rank means we have the maximal, or well, the highest possible value for the rank. Since m is greater than n, the highest possible value of rank A is n. If rank A is n, then we have all the columns are linearly independent. On the other hand, if the columns of A are linearly independent, then the rank of A equals n, since the rank of A is the number of linearly independent columns in there, and there are n columns. AX equals B in Rm has a solution for all B in Rm if and only if ATX equals 0 has only the trivial solution. All right, the if and only if part means that there's two directions to prove here. First, we're going to start with, let's assume that AX equals B, which is in R to the M, has a solution for all B in R to the M. Well, since B is in R to the M, we know that we have 6 rows. A has 6 rows. And we also know that the rank of A plus dim null A has to equal the total number of columns of A, although I don't know what that is yet. I do, however, know that rank A equals rank of A to the T, and since I know that, I also know that rank A to the T plus dim null A to the T equals M, because there are M columns in A to the T, since there were M rows in A. Well, if this is true, if it has a solution for all B in R to the M, since column space of A spans R to the 6th, that's what this means, that we have a solution. The linear combinations here of the columns of A can give us any possible B in R to the M. So column A spans R to the 6th, and column of A is a subspace of R to the 6th. We have the column of A equals R to the 6th. I don't know where I got 6 from, but it spans R to the M, so column of A is equal to R to the M. So then I know that the rank of A equals 6. So rank, I don't know why I keep saying 6. Rank of A equals M, so rank of A to the T also equals M. But then based on this equation here, this implies that the dimension of the null space of A to the T is equal to 0, which means that the only solution to A to the Tx equals 0 is the trivial solution, or is 0, and that takes care of that. Now the other direction, this is, like I said, this is an if and only if. Now we assume that the only solution to A to the Tx equals 0 is the trivial solution. So we are told that dim null A to the T is equal to 0. But now A itself had m rows, so this has m columns. So that we know this implies that the rank A to the T is equal to m, since the rank of A to the T plus the column, the dim null A to the T has to equal m, because that is the number of columns of A to the T, if you like, this is the number of rows in the original matrix. So anyways, but then this implies that rank A also equals m, since it's just the same thing. But here then, you have, this implies that the dimension of the column space of A equals m, but column of A is a subset of R to the 6. So here you have a subset. There's that 6 again. Must be one of the previous examples. So, but column of A is a subset of R to the m, and it has the same dimension as R to the m. So we have to believe, or we have no choice but to determine that the column of A equals R to the m. Well, that continues to imply that AX equals B has a solution for every B in R to the m.